an operator algebraist. So if you ask me hard question about operator algebra, I won't be able to answer. And if you don't like operator algebra, at the end of my talk, I will talk about IRSs. So there will be something interesting for people who are not interested in operator algebra. So the motivation of my talk is to classify operator algebra that arise from dynamics. And in order to motivate all this, let me start with the measurable setting, so measurable dynamics. So the motto of my talk will be that tilings of actions are good to classify operator algebras that comes from the actions. And one very nice theorem in the measurable setting about tilings of actions is the Rocklins type theorem, which is due to Ornstein-Weiss, and which says the following. Take a PMP essentially free action of an amenable group, then you can find the tiling of the space, or an almost tiling of the space, with shapes that are Kerr sets. So for all finite subsets, so this is my notation for finite, of gamma, and for all epsilon, there exists a finite collections where the SI are the shapes, so there are finite subsets in gamma, and the VI are measurable subsets of X, such that the following holds. The SI are F epsilon Fellner, and they are pairwise disjoints, so meaning that the G VI, where G is an element in SI and I is in the finite collections, are pairwise disjoints, and they partition they tile almost all the space. So the measure of this tiling is almost everything. And this Rocklins-type theorem is a powerful theorem. It was mentioned, I think, last week that a consequence of this theorem is that any two PMP free action of gamma amenable are approximately conjugate. Another consequence which would be of interest for me is a theorem due to Kohn, which says something about the von Neumann algebra associated to a PMP essentially free action of an amenable group. So the setting of the theorem is the following. So gamma acting on X mu is a PMP essentially free ergodic action of gamma amenable. And to this, one can associate a von Neumann algebra, which is called the cross products. And Kohn's theorem tells you that this von Neumann algebra is something that is known. So this von Neumann algebra is this guy, and Kohn's theorem tells you that this is the unique factor of type 2-1. So sorry?
Hyperfinite.
Hyperfinite, thank you. Hyperfinite factor, the important word. So if you don't know what all these words mean, the only thing that I want you to remember to get is that whenever you have a PMP action, which is essentially free and ergodic, then there is an abstract object, which is a von Neumann algebra. And if you want to classify this von Neumann algebra, then one good thing to do this is to use tilings And Combs tells you that actually there is only one such object in the measurable setting. The thing that I will be interested in is in the setting of topological dynamics. And in this setting, this is way much wilder. So the goal is the following, is to classify, so this time we don't have finite algebra because we're not in a measurable setting, but we have C-star algebras. And the goal is to classify C-star algebras that arise from topological actions on the Cantor space. So the action will be supposed to be topologically free. Here we had that the action is essentially free in the measurable setting. In our setting, the right thing to assume is that the action is topologically free, meaning that there is a G delta set of points with trivial stabilizer, so free in the topological setting. Minimal being the analog of I got it here with gamma amenable. And X the Cantor sets. So again, when you have such an action, you have an abstract object, which is a C-star algebra, and the C-star algebra is called the cross product and is denoted like this. So this is a C-star algebra. And the goal is to classify these objects as it was done in the measurable setting. The thing is that there is no one unique object in this setting, and there is a wild world of such things. And the thing is trying to understand how two such things are or not the same. And for this, there is a huge program which began in the 80s with Elliott, which produced an invariant. So given a C-star algebra A, Elliott defines an invariant which is defined with K-theory and tracial data. So I'm not going to give you the definition. And the thing is that we want to say that A is classifiable if, so A here is a C-star algebra, and we want to say that A is classifiable if for all other C-star algebra B, A and B have the same Elliott invariance, if and only if A and B are the same. And people in C-star algebra, in classification of C-star algebra, are trying to understand when the Elliott invariant is sufficient to classify C-star algebra.
This is what they want, right?
This is what they want. This is what they want.
This is the definition.
So this is the definition.
Okay, I see.
This is the definition. Yes.
Can you, without going into the definition, to say what kind of object the Elliott invariant is?
So this comes from K-theory. So there is an ordered group.
It's countable stuff, right? Countable structures.
Countable stuff and computable. I mean, one can, given a concrete C-star algebra, one can compute. I mean, in some cases, one can compute the Elliott invariants and try to understand whether Elliott invariants are the same or not.
So this is a Borel map or something, like from A to Elliott A.
I don't know this. I mean, this is. I don't know whether this is Borel or not.
Does it involve a simplex of some sort?
Yeah.
Yeah.
So it's not countable.
Okay, some part of the Elliott invariance is countable, but some others not. You're right. Yeah, it's okay. And so the conjecture is the following. So again, trying to understand the abstract object that comes from topological dynamics. the conjecture is the following: given topologically free minimal counteraction of gamma amenable, then the C-star algebra associated to this object, to this action, is classifiable. So this is the conjecture. And in order to understand this conjecture, to try to prove this conjecture, people have tried to find good notions of tilings in order to imitate what happens in the measurable world. So people have tried to find good notions of tilings of actions in order to try to get this conjecture. So now let's talk about tilings in the topological setting. So here is the definition, which is due to Matthieu and Kerr in the general setting. So take a counter action, or an action on a counter set of gamma amenable. Such an action is called almost finite if the following holds. If for all finite sets and for all epsilon, again, there exists a finite collection where the SI are finite subsets of gamma being F epsilon Fellner. So this is the shapes of the tiling. And the VI are Klopen subsets of X, such that, again, this is a tiling, meaning that the pieces are pairwise disjoints. And this time, we require that this tiling covers the whole space. So this is the definition of dynamical tiling that I will talk about in this talk. And the thing is that this is a nice property in order to classify C-star algebra that comes from topological dynamic. Before I talk about it, let me make a small pause and talk about freeness, because there are several notions of freeness in this talk, and I think it's good that you really understand what's going on. So take an action, so counter minimal action, so minimal action on the counter set and take mu, a gamma invariant probability measure on X, which is ergodic. Then we have three notions of freeness. The strongest is that the action is genuinely free, meaning that no points have non-trivial. I mean, every point has the trivial stabilizer. So here, the stabilizer of each point is the trivial group. Now we have the notion of mu essential freeness, meaning that on a set of full measure points have trivial stabilizer. And now we have the notion of topological freeness, which is on the G delta dense set, points have trivial stabilizer. And we have these implications, and the converse implication does not hold in general. All right, so let's go back to dynamical tilings and classifications of C-star algebras. So this definition is good for classifying C-star algebras. So here is the theorem of Kerr. So it says the following: if you have a counter minimal action, which is free, then almost finiteness implies that the C-star algebra is classifiable. So we're good. We have the good definition of dynamical tiling, which gives us that the abstract system, I mean, the C-star algebra associated to the action is understandable, is classifiable. And so what people tried and succeed to do in the last years is to find good classes of groups whose Cantor minimal free actions are all almost finite. So here is a bunch of theorem. So gamma is a free Cantor minimal action, and it is almost finite when first theorem gamma is sub-exponential growth. So this is due to Dornarowitz and Zhang. So every free minimal counteraction of a sub-exponential growth group is almost finite. Good. So we get a bunch of C-star algebra coming from topological dynamics that are classifiable. Okay. Another result, gamma belongs to some solvable groups, and this is, for instance, the Lamplighter group, and this is a result due to Conway, Jackson, Marx, Stewart, and Tucker-Drob. Marx, Stewart, Tucker-Drob. So they have some class of solvable groups for which every free Cantor minimal action is almost finite, and thus the C-star algebra is classifiable with Kerr results. And a very recent result is that almost finiteness holds when gamma is elementary amenable, and this is due to Kerr and Marishkin. Right, so we have a lot of examples of groups whose free minimal counteractions are all almost finite, and thus whose cross products associated with free minimal counteractions are all classifiable. Right, good. The thing is that in all this setting, the actions are always assumed to be free. And it should be true. I mean, this is what people in the community believe. It should be true that some, or maybe all, of the above results, it should be true that some of the above results hold for gamma being not free, but essentially free for all the invariant measures. Essentially free for all invariants of measure. So the thing is, people are not expecting these results to be way much harder when the actions are only supposed to be essentially free for all invariant measures, whereas being genuinely free. But the thing, so
why don't they think it would be true for topologically free?
This is my point.
Okay.
This is what I'm going to say. So there are some, I mean, there are evidence that this should be true. Okay, and the fact is the following. So here is a fact, or maybe an exercise for those who want to understand better this notion of almost finiteness. This is really an exercise. If gamma acting on X is almost finite, then for all invariant measures, the action is mu essentially free. So putting all this together, we have this conjecture that topologically free minimal counteractions should give C-star algebras that are classifiable. We have all these results which holds when the actions are free, and they should also be true when the actions are essentially free for all the measures. So the question is, for topologically free minimal counteraction of an amenable group, is it true that all the measures are essentially free? So the question is the following.
You mean it's like this arrow can be reversed?
Yeah, whether this arrow can be reversed. I mean, we have the conjecture that should hold in this setting. We have all the work that has been done in this setting, but all this work should be true without being not that hard in this setting. So are these two things the same? So the question is the following. So if gamma beyond x is a topologically free minimal counteraction of gamma amenable, is it essentially free for all, for mu essentially free for all gamma invariant probability measures? And the answer is no. Here is a theorem. Let lambda be finitely generated nilpotent Cauchy-free group, and let lambda being the wreath product of z to the d, that gamma will be the wreath product of z to the d with lambda, then there exists a sequence of finite index subgroups such that at each step gamma acts on the quotients on the finite quotient gamma mod gamma n. And these actions factor onto each other, so one can look at the projective limit of all these things. This is a profinite action, and one can equip all this finite set with the uniform probability measure on it. And so there exists a finite index, a sequence of finite index subgroups such that this action, so this is always a counter minimal action, so is topologically free counter minimal action, which is not essentially free. And here there is only one invariant measure. So when I say not essentially free, with respect to the unique invariant measure. And so these actions are not under finite. So they don't satisfy this dynamical tiling definition. And we don't know anything about the classifiability of the C-star algebra for this kind of actions. So I have, what, 1 minute left?
Yes.
Okay, so I promised that I talked a little bit about IRSs. So this when you have an action which is not essentially free, then you have an IRS, and these IRSs have the property that they're not confined, meaning that so such an action gives an IRS, and this IRS have the property that the trivial, so this is a notion that we already seen in last week and at the beginning of this week, this notion of confinement. This IRS is not confined in the sense that the support of the IRS contains the trivial group, but is not equal to it. And let me finish my talk with a small advertisement. So this notion of groups that admit actions that are topologically free but not essentially free is something that I'm interested in. And the question is, so this is the notion that I call allostery. And the question is, what kind of groups, countable groups, admit actions, so minimal actions on some compact space, which are topologically free but not essentially free. And the thing is that there's not much examples known of such groups, of groups admitting such actions.
Even non-amenable ones?
There are non-amenable ones. These are the first examples of amenable ones. But I mean, there are a lot of groups that are known not to have this kind of properties, but not that much of groups admitting such actions, such allosteric actions. All right, thank you very much.
Questions from Matthieu?
I'm curious how important it is for X to be a Cantor. So like if you replace like X with another topological space.
So this is something that I don't understand because I'm not a C-star algebraist, but there are there are examples of minimal actions on some space with big dimensions, so topological dimensions, for instance, which are not almost finite. And the thing is that the conjecture is that the right setting for which this should hold is that the action have mean dimension 0. So mean dimension is an invariant associated with topological dynamics, and this always holds when the space have topological dimension 0. So your Cantor space. But this conjecture is more general. So the right setting is that the action is supposed to have mean dimension 0.
I mean, to begin with, we require these VIs to be closed sets. So like there better be closed sets.
The thing is that there is this definition holds in
change it.
Yeah, this definition holds in the when the space has topological dimension 0. Kerr's definition is much more general than this and holds in when X is any compact symmetric space.
And these assumptions have to do with simplicity of
the simplicity is the simplicity of the C-star algebra comes from the fact that the action is topologically free and minimal. So for those who know a little bit about C-star algebra, when you have an action on a compact space which is topologically free and minimal, then the C-star algebra, the cross product is simple. It has no ideals, non-trivial ideals, and the fact that the action is amenable, or the group is amenable, implies that this C-star algebra is nuclear, and this is the right setting in which people classify C-star algebras.
Assume that this difference of finite indexable, the intersection of them is trivial.
Yeah.
And so is it easy to see that one in the support, like it's because they can you say a word about this?
You will give the question.
If you can say like that, if it's short arguments to show why the identity is able to the support of this.
So the thing is that so let's talk a little bit about URSs. When you have an action on a compact space, you have a URS. And Ornstein-Weiss tells you that the action is topologically free if and only if the URS is trivial. And the thing is that the URS is always, so in our case, the URS is trivial because the action is topologically free. And the fact is that the URS is always contained in the support of the URS, of the IRS, sorry. So if you want, here I should have written the following. So the URS of the action is equal to 1 because the action is topologically free.
So the fact the action is topologically follows from the follows on the fact that the intersection of one of these and in the sum is
so the action is topologically free by Ornstein-Weiss. The URS is trivial, and the fact is that the URS is always contained in the support of the IRS, and that's why we have this.
Maybe you already said this, but are there groups where you can know that the multiplication universes are topologically different places?
Yes, a lot. Finitely generated nilpotent groups, polycyclic groups, high rank lattices, and so on and so on. This is Stuxzimmer here. I have tons of other examples. If you want to discuss this later on, I'll be very happy to.
I think we're saying this here that example is topological free but not essentially free. Or it's the Reese product of the CP.
That's important.
Yeah, okay.
Okay, so we have now coffee break and we meet at 11:30 and 10.